Flammia. His no introduction, has been in quantum before, probably more. And he's been long obsessed with SIC-POVMs. And this is a recent, very seminal, I guess, result that will have a lot of new math, at least for me, maybe for some of you. And I encourage you to pay attention because he's going to be a great presenter. I'm going to set the standard really high. And so take it away, Steve.
Thanks, Victor. Yeah, this is a problem I've been thinking about for a very long time. It's the very first thing that I ever thought about when I started in graduate school. And my advisor has joined this call, so I have to impress him, Carl Caves. This is joint work with Marcus Appleby and Gene Kopp. This is a long paper. It's like 180 pages. We've been working on this for several years now. There is a lot of mathy stuff in here. Some of the math will be unfamiliar to most of you, but this is a broadly accessible talk. And also we spent a long time writing the introduction to this paper in such a way that's hopefully accessible. So if you want to go just a little deeper, I don't recommend anybody goes too deep because this problem is kind of a killer. But if you want to learn a little bit more, the introduction is, I tried really hard to make it accessible. So it should be readable. So let me first define what these things are that are part of the main result of this work. So SIC-POVMs are defined to be rank 1 POVMs. So a set of d-squared rank 1 projectors. Sorry, this is equivalent to having a rank 1 POVM if I just normalize these things appropriately. So I just get a collection of d-squared rank 1 projectors, Hermitian projectors, such that their pairwise Hilbert-Schmidt inner product is 1 over d plus 1. So an example of that, if I plot the block vectors of these projectors for the case d equals 2, I can get just 4 points on a regular tetrahedron. And I put those 4 points on the surface of the block sphere. And when I do that, I have an example of this for d equals 2, right? D squared for d equals 2 is 4. I got 4 points. The inner product between these vectors is related to the squared inner product of the associated like pure state vectors. And you do the math and you get this number, you get like 1/3. Okay, so that's an example of one of these SIC-POVMs. So why are these things interesting? So they're geometrically elegant, but they also pop up as optimal constructions in a lot of, perhaps a surprisingly large number of places. So they're the maximal number of complex equiangular lines. I can think of this rank 1 projector as defining a line in complex projective space. So this is like a maximal number of equiangular lines that I can have in d dimensions. They're a complex projective 2 design, which is minimal. That is, like all designs, these are state designs, not unitary designs, which are probably more familiar to this audience. But if I average any degree 2 polynomial over the uniform measure on the surface of a complex sphere, then it's the same as if I just take the discrete average over those points, the d squared points in the SIC. There are lots of other extremal criteria that they satisfy. They're maximal equiangular tight frames. It's okay if you don't know what all these things are. It's more just to give you some flavor that these things appear in a lot of different places. They saturate the Welch bound for k equals 2. They give you the optimal norm constant relating the Euclidean norm with the Gowers uniformity norm for the group Z mod D.
They're pretty accessible.
Like I said, you don't have to know what these things are. You don't have to know. Well, you know what a design is, right? So that's why I highlighted that one especially. Do you know what a tomography is? All right. So they give you for some specific loss function, they give you like an optimal measurement for quantum state tomography. They give you an improved key rate for certain QKD schemes. They increase the efficiency of shadow estimation. This is an experimental paper, in fact. So they appear in a lot of contexts. But do these things even exist? Well, we saw on the last slide, they exist for d equals 2. Do they exist more generally than this? So in 1999, Gerhard Zauner conjectured, he actually conjectured something stronger than this, but he conjectured that SICs exist in every dimension D, okay? And there are there's a lot of numerical evidence, starting with Zauner himself, who had some exact constructions and some numerical constructions up to, I think, dimension 8, So people have constructed examples, exact examples, meaning like exact using a computer algebra package in a lot of small dimensions up to 53. And people have constructed numerical solutions in many more dimensions, all dimensions up to 193, and several higher dimensions as well. However, there are only finitely many dimensions to date that are known where SICs are provably exist, even sort of a numerical proof. There's also a 2025 euro prize as of this recording for finding an infinite family. It goes up every year, actually. Okay.
It's open.
It's still open after this talk. Yeah. The prize is open, yeah, because we didn't prove the result is going to be a conditional construction. It's conditional on some conjectures, so I don't have a proof.
So you're saying people don't even have like an infinite family?
No, there's no infinite family known.
I'm not familiar with the term infinite family. Does it mean your Hilbert space is infinite?
It just means let D be any dimension greater than 1. If you can find an infinite sequence of dimensions where you can prove that these things exist, you win 2,000 euros.
Even if you skip some dimension.
Yeah, that's right. Yeah, it could be like
I
all,
see.
it could be like 2,
Even
4,
ones or
8,
something. Okay.
or all the even dimensions, or even, yeah, like it could be all twin prime dimensions or something. Like, I don't know, like, you know, it could be anything that's like
Some number
some,
theorists can think of.
yeah, that's right. Yeah,
Hardest way to win $2,000.
euros. So, yeah.
Just
Okay, so I'm going to specialize the discussion a little bit to put some symmetry on these objects, because it turns out, with exactly one exception, which is kind of special, it has to do with quaternions in some weird way, and nobody really knows if this thing is part of a family or if it's like just some weird exceptional thing, the way sort of exceptional groups are sort of odd objects. So with only one exception, every SIC is covariant. I'll explain what that means with respect to the Qdit-Pally group or Weil-Heisenberg group. So this is just the group of like Qdit shift and phase operators. So I have like a dth root of unity, and it turns out to be convenient to take minus the square root of that as the generator for the center. And then I can shift, or I can shift in phase. And then I look at the group generated by those two operations. Okay, so this is like the Qdit-Pally group or Weil-Heisenberg group. If I look at the conjugation action on states, then this overall phase doesn't matter. And then this action is actually abelian. Okay, so in fact, if I mod out this center, this phase, then I just get the group Z mod D cross Z mod D, right? So I get 2 copies of the cyclic group mod D. Okay, so what does covariant mean? It just means that these SICs are generated as the group orbit of the action of these displacement operators, okay? So I just take some initial rank 1 projector and I conjugate it by all of these different displacements. This choice of phase here is conventional, but it makes the math work out nice. So I look at all the shift and phase displacements. That generates d squared points, and all such constructions are always group orbits in this sense, okay? So the problem now reduces to just finding this fiducial vector. There's an obvious unitary equivalence to this problem, right? So like if you go back to the definition of this equiangularity, if I conjugate everybody by the same unitary, that's just a basis change in the Hilbert space. That's not going to change this equiangular property. So that's kind of an uninteresting feature. So I would like to separate these things into unitary equivalence classes. Once I fix this Weil-Heisenberg covariance, then unitary equivalence splits into equivalence classes based on a Clifford group. So there's a Qdit Clifford group. And there's something called the extended one, where I also allow complex conjugation in the computational basis. Is like a natural symmetry that happens to pop out. But basically, you can think of, once I fix the Qdit-Pally group, the remaining symmetry is like the Qdit Clifford group. Okay, and that will define some equivalence classes of these objects. So we'd like to understand, do these objects exist? And we'd like to study and understand their symmetries and equivalence classes. Okay, so for the rest of this talk, when I say a SIC, I'm always talking about a Weil-Heisenberg covariant SIC. And furthermore, I'm going to eliminate certain small dimensional pathological examples by saying D is greater than 3. Okay, so d equals 2 and 3 are special, and I'll ignore them.
So you said that now it reduces to finding this pi zero. What
Mhm.
property should it satisfy?
Well, it has to have the property that all the other elements in the group orbit have to have the same overlap,
Oh,
right? So like this
I see.
equiangular
Sure, but
condition,
it's kind of hard to check. I see.
well, you'd have to check all d squared displacements.
Oh, I see. Okay.
And so there's d squared conditions on this like rank 1 projector. So, and then d is large. And then you have to do this, like if you want to win the prize, you got to get it for all d in some sense, right? The conjecture is you can always do this.
We'll carry on for 45 minutes.
Yeah. Okay. Our main result is a construction of these objects in every dimension, but it's conditional on 2 conjectures. One of them is called, it's a specific thing, a specific Stark conjecture. There's a family of conjectures called the Stark conjectures. And the other is a special function identity that we call the twisted convolution conjecture. So the main result is that assuming the Stark conjecture and the twisted convolution conjecture, Zauner's conjecture is true, moreover, via an explicit construction. Okay, so we have like a formula that you can evaluate. Well, actually, the notion of construction here is a little bit strange, and we'll go into that. It's maybe not strange if you're a number theorist, but it's strange for anybody who's used to sort of a smooth object. Okay. So now once we impose this symmetry that we get from the QDit-Pally group, you can prove that this projector, this fiducial projector, has to have the following form. So the displacement operators form a matrix basis. So I can expand any matrix as a sum over coefficients times displacement operators. And if I enforce this defining condition that I get for SIC-POVMs, that they're equiangular, then I can say, well, it's a rank 1 projector, so its trace is 1. So I get 1 over d times the identity, plus some constant times some expansion coefficients that satisfy 2 notable properties. One, I get from hermiticity, which is that if this operator is Hermitian, then nu sub p, this expansion coefficient, times nu minus p has to be 1. And the other, from equiangularity, I get that these nu p's have to be complex unit phases. So they're just numbers that live on the unit circle. So this is a consequence, a straightforward consequence of plugging in the displacement operator basis to this equiangular condition.
The displacement is this x to the p's to the next to the p1.
Yeah, they're the QDit displacement operators, like the finite QDit displacement operators. There's no bosons here or something. I know Alexi's like a real physicist, so he's going to ask me hard questions.
Where's the Hamiltonian?
You take the log of the unitaries. Okay. So a long series of works. I'm going to explain, if you, like I said, like you don't have to understand all the words. So I'm going to try to give some flavor here. A long series of works studying all of these. So, okay, you might have thought actually when I showed you what the sort of present state of knowledge was, people have constructed these things in the first 50 dimensions. So like, what's the problem? You know, just look at the first 50 examples. You can't guess the pattern from the first 50 examples. Like, what's wrong with you? What have you people been doing for 25 years? Why is this even open? It was really not obvious what the patterns were. And it took a very long time before the following insights had been distilled, that these numbers, nu sub p, are extremely special. And we now understand, culminating from a long series of works, that they are basically Galois conjugates, I'll explain what that is, of things called Stark units over Q adjoins square root of delta. Okay, so this is like rational numbers of the form a rational number plus a rational number times square root of delta, where delta is this number right here, d plus 1 times d minus 3. Okay, so like rational linear combinations of like a rational number plus a rational number times square root of delta. And so they're units in this number field. Okay. So a Galois automorphism is something you may not realize, but you're all familiar with it because complex conjugation is an example of a Galois automorphism. It's a Galois automorphism where you think of the real numbers adjoining the complex unit I, square root of minus 1. And I can just take I to minus I and do complex conjugation. That's an example of a Galois automorphism, right? It fixes the real numbers, but it flips the sign of I. So here, root 2 is behaving like I, And A and B are not real numbers, but rather rational numbers. And so if I apply Galois automorphism, I take A plus B times root 2 to A minus B times root 2. Okay, so that's what a Galois automorphism is. It like distributes over addition. It's sort of like a Q linear operation, but it is not an R linear operation. We'll get back to that. So you know what, you have an intuitive sense at the very least of what Galois conjugation is. But what are Stark units and why are they special? So I'll say a little bit about what the Stark conjectures are, just to give you some flavor of the types of questions that they illuminate in mathematics. And at the most basic level, the Stark conjectures, and it's closely related to an open Hilbert problem, Hilbert's 12th problem, assert that certain special points of transcendental functions are actually algebraic, meaning polynomial, right? Algebraic basically means polynomial, okay? So you're all familiar with this too, even though you may not know it from the way I'm describing this language here. To say it in slightly more detail, basically, it's a conjectured relationship between certain analytic properties of things called zeta functions or L functions. So we've all heard of the Riemann zeta function, which is like you sum over the integers 1 over n to the power s. There's slightly more general things that you can write down that are still called zeta functions. And there's other related things called L functions. You can study analytic properties of these functions and relate them to arithmetic properties of certain algebraic number fields. Okay, so like the Riemann zeta function is related to the distribution of primes in standard integers. These other things are related to other more general arithmetic quantities when you study these algebraic number fields, like Q adjoining square root of 2 was the example we had on the last slide. Okay, so there's other arithmetic questions that you can ask in those other number fields. And the Stark conjectures illuminate the structure of arithmetic in those fields. We don't actually need the full power of the Stark conjectures. We just need one special case, the order 1 abelian Stark conjecture for real quadratic fields. Okay, you don't have to know what that is. I'll give you a little bit more flavor into the types of questions that these things are designed to address. And again, it will show you that actually you're more familiar with this than you might think. So one example would be, I forgot to mention, whenever you define one of these number fields, right? I mean, for the complex numbers defined as an extension of the rationals, you say, well, I'm going to define I to be the root of x squared plus 1 equals 0. Right? And then I'm going to append that root to the real numbers. That gives me the complex numbers. Okay. But there's a symmetry there. I could have appended minus I and I would have gotten the same algebraic structure. Okay, so that relationship is this Galois automorphism. And more generally, the set of Galois automorphisms generates a group called the Galois group. Okay. People are very interested in when these groups are abelian because it's closely related to solvability of equations. Okay, Galois' name is maybe synonymous with solvability of equations, as many of you have probably heard. Okay, so I introduced a technical term here that I forgot to explain: abelian extensions. That just means that the sort of symmetries of these defining polynomials are abelian or solvable or nice. If you just want an adjective, they're nice. So if I start with rational numbers, okay, and I ask what are the polynomials that I can add where the symmetries are abelian, then it's things where the roots are just these roots of unity evaluated at rational points, right? It's like I take this exponential map, e to the 2 pi I z, I evaluate it at a rational number. So if I pick a general point on the unit circle, I will generally just get a transcendental number out. But if I evaluate it at a rational angle, right, a rational multiple of 2 pi, then I get an algebraic equation, right? So we all know that if I sum up all the powers, if I take a rational number with denominator n, and I sum up the first n powers, right, that's like a geometric series that closes on itself, I'm going to get 0, right? So in fact, those things satisfy a polynomial equation, despite the fact that in general, these points do not satisfy any polynomial equations. So all of the points where I evaluate z at a rational number are very special from the perspective of the generic points that I could have put in elsewhere in the complex plane to this exponential map. So I have a transcendental function. I evaluate it at a special point, and like the entire power series of that transcendental function like truncates at some finite order, and I get a polynomial equation. It's a bit miraculous, but actually it's kind of mundane when it's just this unit circle example, because we all know that like, you know, cosine 45 degrees or whatever is like whatever √2 or something, right? Like it's like, and that's has a quadratic equation that specifies 1 on √2. So it's kind of mundane from that sense, but these star conjectures are quite deep because they're studying the properties of which functions and which points have this property. Okay, so this is a simple example of this. And another example, which is more complicated, are so-called torsion points of elliptic curves with complex multiplication. So maybe I'll just leave that up there. You can ask me if you want more detail about that. They come about when instead of thinking about rational numbers, I think about rational numbers with an imaginary quadratic extension. We actually are going to need, remember we had this number delta, which was a positive quadratic irrational number. So we actually need the first unproven case of these star conjectures is for real quadratic fields. These two cases are somehow the only known cases where these conjectures have been proven. Okay, so that's all I'm really going to say about the star conjectures. Basically, everything that I'm going to say from here on out is assuming the order 1 abelian star conjecture for real quadratic fields. So if I say we know, it's always we know conditional on assuming that. Okay.
That's super question. So you kind of listed it like a few slides ago, like you can figure out what the pattern is. Not here. That's great.
Yeah.
The next slide. Yeah. So people figure out what the pattern is. So can they now use the pattern, check if, you know, or 157 and whatever.
We'll see. We'll get there. We'll get there. We'll get there. Good question. So, okay, let me just show this formula again. This is equivalent to the defining property for these SICs. So we have these expansion coefficients. They have to be phases. And because of equiangular property, the defining property of SICs, and hermiticity enforces this. Okay. So now, so we mentioned that this long line of work culminated in showing that in every example, these complex phases are conjugates, Galois conjugates of Stark units. Okay, so let me say a little bit more about these Stark units. And I've plotted an example here for the special case d equals 4. So these 4 points turn out to be the phases that you get when you solve these equations for d equals 4. And the Stark units that you get, which are Galois conjugates of those red points, are these blue points here. Okay. And you can write these things down as roots of polynomials because they're algebraic numbers. Algebraic number means it's a root of a polynomial. And I should have said like this magic number. So if you plug in d equals 4, this magic number delta that we said was d plus 1 times d minus 3. So 4 plus 1 is 5 times 4 minus 3 is 1 is 5. So we indeed see root 5 popping out here. So there are two types of symmetries here. Galois conjugate that exchanges blue with red. Okay, and that takes me from these Stark units in blue to these special numbers, these phases in red. There are also, and we'll talk about these later, there are symmetries that map red to red and blue to blue separately. Those are also Galois symmetries that we also will care about a little bit. But what we would like to do is study this blue polynomial, find a formula for these blue values, and then apply this sign switch to go from delta, take root 5 in this case and flip it to minus root 5. So the minus cancels. And then we're over here in red world, and then we can solve the problem. That's what we'd like to do. Okay. By the way, notice the product of these two things gets rid of the root 5s, and you get like all rational coefficients, integer coefficients in back. Okay. So these observations lead us to defining a new object, which is like a dual object, a Galois dual object, which we call a ghost. Because when we sort of figured this out, it was like very mysterious. So what is a ghost? I've just taken the previous definition and I've modified it slightly. Instead of calling it nu, I call it u. And instead of making them complex unit phases, I make them real numbers because all Stark units are real numbers. So I'm going to say they're real numbers. And instead of hermiticity, this property here is actually preserved by this Galois conjugation map. So this property is left unchanged. Okay, but I lose hermiticity in general. In fact, you can prove that they're always non-Hermitian. Okay, so I've just said, instead of complex phases, I insist that they're real numbers, but they still have to obey this condition. Okay, which I inherited from hermeticity over in the sort of SIC world.
Can you modify the inner product to make these SICs on some non-Grecian world?
I don't know. Maybe, but maybe.
And you're saying they're still projectors after you've replaced these phases with real?
They will be, yes, because the rank here will be preserved when I Galois conjugate. Yeah, no, this is crazy. It gets crazier. Okay. So now we have a plan now, which is we're going to try to find these U sub p's. And then we're going to say, well, I just need to find, I have this Galois automorphism. I know this magic number delta. I'm going to apply the Galois automorphism to this guy that I've just constructed somehow, hopefully, and I'll get pi, and then I'm done. I collect my 2,000 euros, and I'm happy.
More than 2,000. You will have found
Yeah.
all of them, and not just.
Well, yeah. Anyway, okay.
It actually- it could be 2,000
Well, we'll
for
see.
every-
We'll see how close we get to this. Okay. So we can construct these ghosts conditionally. Okay. And we can, they come with labels. Okay. And I'll say a little bit about what these labels are. We call these labels admissible pairs. Okay. So this classification is wonderful because it feels like we sort of finally understand this problem. All of these 1 through 53 examples that people had studied exhaustively, people were able to study what the symmetry groups were of these different SICs and all various other properties of these things. And it looked like a hodgepodge of stuff that didn't make a lot of sense. And these admissible pairs sort of explain all of that. So an admissible pair is two things. It's a dimension D and a binary quadratic form. So I just mean like a degree 2 polynomial in 2 variables, which I can either write in this notation here or in this shorthand notation, ABC. Okay. And we say that a pair is admissible if this magic number delta divided by the discriminant of Q. So remember, the discriminant of a binary quadratic form is the same as the discriminant of the quadratic equation that you get. It's just b squared minus 4ac. It's like the thing under the square root. So I take delta divided by the discriminant of Q. That should be a perfect square. Okay. And the integer whose square is that ratio, f, we call the conductor. And we call k equals q adjoin square root of delta the associated field. Okay, so an admissible pair is really just a dimension D and a binary quadratic form that has some specific choice of discriminant. Okay, it has to have some kind of divisibility or integrality constraint on it.
Where did the binary come from?
Binary, it comes essentially from the fact that there's like an X and a Z. And so there's like 2 different shifts that you can do. And this is closely related to the fact that like the Clifford group and the Pally group, it's like a 2x2 matrix group, basically. And so it's related to the fact that there's only 2 things. There's X and there's Z.
Qubits. It's not right.
Qubits.
It's not.
Yeah, but it's single particle qubit, not n qubits, where it would be a 2n by 2n symplectic matrix.
Oh, simplex. Okay.
Yeah, like
You're
the SL2Z, well,
Alright.
the Clifford groups are the symplectics.
Yes,
So-
yes. You're in the symplectic representation.
Yes,
I'm
it's
in-
all clear now for Victor. Okay. Okay, so I had mentioned this idea of equivalence relations between these objects. So we can study unitary and anti-unitary. Anti-unitary just means we apply a unitary and we also complex conjugate in the standard basis. So there's equivalence relations between these ghosts, and it's closely related to equivalence under similarity transforms of the defining quadratic forms for these pairs. In general, we have a many-to-one map from the set of admissible pairs to the set of ghosts in dimension D. And we can say something quite concrete about this. So ghosts are unitarily equivalent if and only if the corresponding forms are equivalent under similarity transform. So if I take Q and I take a GL2Z matrix, so if this said SL2, these would be like Cliffords. But with G, it's a little more general. But of course, GL can only have determinant plus or minus 1. Anyway, we can talk more about that later if you want, Victor. I just say, like, take one of these GL2Z matrices, L transpose QL is a similarity transform on that. And then two ghosts are unitarily equivalent if and only if their associated quadratic forms are equivalent under this transformation. Two of them are equivalent up to a conjugation, which is like a red preserving and blue preserving conjugation, not one that exchanges red and blue, but one that preserves red and blue. If and only if the corresponding forms have the same discriminant. Okay, so in general, there can be more than one discriminant here. Okay, the set of ghosts corresponding to all forms of a given discriminant is called a multuplet. And for a long time, people had no idea where these multuplet structures were coming from. We can now explain this. So here, I think it's time we do an example. In D equals 35, this magic number, delta, D minus 3 times D plus 1 is 1,152. So I'm looking for quadratic forms that have a discriminant such that delta divided by this, basically it's like a square times this, sorry, that this number is a squared after I divide out the discriminant of the quadratic form. Okay, so there's some like divisibility constraint on the quadratic forms. It has to be positive and it has to divide this, so there's only a finite number of these things. And they split into classes. And this number F is like the square thing, right? So here's a form 2 minus 4, 1. And here's another one, 1 minus 6, 1, where the square in front is F. So you can compute like B squared minus 4AC to get the discriminant of Q. You can check that it all works out. And so for like these multuplet structures, so this diagram on the left is just taken from an old paper where people had no idea what the heck was going on. And they gave these things labels like B, C, D, because we didn't know what the heck these things were. And now we know that they're labeled by these quadratic forms, or at least actually equivalence classes of these quadratic forms. Okay, so I want to show you a little bit about the formula that we use. So once you've specified one of these admissible pairs, you have to actually compute the associated ghost. So that's the label for it, but now you need a formula that tells you how to compute the ghost. So I won't be able to show you the complete formula, but I'll show you the kind of genesis of the formula. So it's related to this thing called the Shintani-Faddeev modular cocycle. Big word, but it can be defined as a ratio of this thing, which is called a Q-Pockhammer symbol. If the imaginary part of this number tau is a complex number, if the imaginary part of this number tau is positive, then this infinite product converges, okay? And this thing is analytic in the upper half plane. If I add some conditions on, so if I pick an element A of the group SL2Z, and it satisfies some congruence condition with respect to D, then I take certain ratios of these things to define this new object, this Shintani-Faddeev modular cocycle. This symbol here is the Hebrew letter shin. And here this action A is like a linear fractional action. So this is relatively explicit. I don't expect you to like be like, oh yeah, obviously that's the formula. I just wanted to show you that like there's an explicit formula. Now I'm cheating a little bit because we actually need the analytic continuation of this to the real axis and things get more complicated. But you know, this fits on a slide and it's relatively uncomplicated. Okay.
And you will construct only sort of one member for like.
Well, you'll have to pick an A. And then as you iterate over P, it's like generating the group orbit of this thing. So like you fix an A, which you derive from this pair, the admissible pair DQ. From that, you derive an A, okay? And you derive a tau.
And I'm just saying for the, like for D equals 35, and many solutions, will we get all of them or just one?
We conjecture all of them. We conjecture that this is a complete classification. So we have a many-to-one map and we can conditionally prove based on only this star conjecture that we get that always gives you a solution. We can't, you need a slightly stronger conjecture but we think that it gives us all, like every solution is of this
But
form.
what do you vary here to cycle through
Different
different
Qs with different discriminants and ones that have the same discriminant but are in different similarity classes.
And you have constructions for these Qs, you know how to look for them, so this.
Yeah. I'll show you like code that does this even. So yeah, given a D and a Q, you compute an A and a tau, and then you loop over all Ps, and then that gives you the ghost. And then you pick a different Q, and you can derive a different A and tau, and then that gives you a different ghost if it's in a different similarity orbit or a different discriminant. Yeah.
When to stop looping all for all P.
Well, P is only between 0 and D-1 in each coordinate. It's like, it's labeling the different displacements. So P is labeling on displacement. I say in Z squared, but really it's mod, it only matters mod D. This thing has a period modulo D.
Yeah.
Okay. So, you know, we compute this number A by considering a specific group. So the quadratic form that defines this admissible pair has like a stabilizer group under similarity, subject to this congruence condition. And if I pick a generator of this group, it turns out it's cyclic. If I pick a generator of this group, that's A. And if I pick a root of this quadratic form, so I take that quadratic form, which is like ABC, and I take B minus square root of B squared minus 4AC over 2A. That's like some root of this quadratic equation. Then that's how I get this object. I can just compute it. And this thing I'm not being explicit about, but we have an explicit and easy to calculate formula in the paper. It's kind of messy, but it's straightforward. That's it. That's the formula for these things. Okay. I mean, why didn't we guess this before, right? Pretty obvious. No, it was very not obvious. So I will give everybody, this isn't in the paper, but if you sort of boil this down to the simplest possible example, there's a really nice and simple example that's sort of uniform. It exists in every dimension. There's no sort of weird number theory, like inhomogeneity. I can say for every D, I can define the following quadratic form: 1 minus D, 1. So you can just check from B squared minus 4AC is the discriminant of this quadratic form. If you plug this in and you plug in what you get for delta is D plus 1 times D minus 3, you can check that this is always satisfying the admissible pair conditions. Okay. Huh?
What is F?
It's the largest square that divides it. It's whatever it is. I don't even compute it.
It's not just a simple function of D.
It will be, yes, but you have,
well.
well, you can work it out. I didn't have it on the slide, and I'm not about to try to do arithmetic on the fly. That's like a recipe for embarrassment.
I thought you.
Even more embarrassing than dodging the question would be if I tried to like do division on the fly. Okay. So this thing is like uniformly defined for every D. Okay. And we call this the principal maximal ghost because this is the so-called principal quadratic form. And this F number is maximal among all the Fs that you could have. Okay. So here's the construction, getting rid of this Shin function and various complications with like SL2Z and stuff. I pick two numbers, P0 and P1. I just pick them between 0 and D-1. They're integers. Okay. And then I pick a third number, P2, which is also in the interval 0 to D-1, such that P0 plus P1 plus P2 is 0 mod D. Okay. And then this is the root that I get of this form. Okay. I'm going to define one more number. This is a quadratic irrationality. It's a quadratically irrational number because rho is a square root of a quadratic equation. And these P's are just integers. So this is like a rational linear combination of like, it's a rational number plus a rational number times square root of delta. This index arithmetic here is cyclic mod D. If those of you have heard of this before, maybe you've looked at some of these papers, this cyclic mod 3 symmetry here is this famous Zauner symmetry, which is very cool. So this is the formula. Like you plug all that stuff in, you do the analytic continuation, you simplify things, then this is the formula where P is like the first two of these coordinates, P0, P1. Okay. So you can see it's not as nice as you might hope if you want to actually prove unconditionally that this gives you a solution, right? Because like, how are you going to prove that this satisfies all the conditions that you want? It's kind of messy. There's an integral here, for example. But assuming the Stark conjecture and this other twisted convolution conjecture, which I'll say more about in a minute, this gives a conjectural ghost fiducial projector, which then all I have to do is conjugate it, and I get the SIC fiducial projector. Okay, so there it is. It's glorious. Okay. Now, I didn't say much about it, but the twisted convolution conjecture, if you write it out in terms of these variables, we don't phrase it this way in the paper because we needed it in a slightly different form. But it basically boils down to the statement that this thing is, in fact, a projector. So we can prove that equiangularity follows, but we can't prove that the thing is like idempotent, that like epsilon squared is epsilon, which is very frustrating. It doesn't feel like that should be as hard as the equiangularity condition, but we couldn't prove it. So we just, in a good tradition of people who can't prove things, we just add it as a conjecture, and there it is. So yeah, it basically boils down to the statement. So this is the conjecture. We would love to be able to prove this. We don't know how to prove it at present.
C, what was that?
Sorry?
C?
Oh, C is this square root of the root of unity that you get for D. It's like the Dth root of unity, but then you take minus the square root of that because that's like a nicer polarization or whatever for the Q-date Clifford group. Sorry, the Q-date Pally group than if you just have the roots of unity. It turns out to be a slightly nicer formula.
For all D, okay.
Yeah. It's just a Dth root of unity. Oh, sorry, and I didn't say what that is. That's like P1 times R2 minus P2 times R1. It's like the twisted like symplectic inner product. Yeah.
Can you check this conjecture numerically up to whatever 153?
Yes. Yes. Okay, so to recap, now we have this formula. We've assumed the Stark conjecture. So we now know that these U sub P's are like actually algebraic objects. So, and we assumed the twisted convolution conjecture. So this thing is a projector. So all we have to do is apply this Galois automorphism, flip the sign of root delta, and we're done, right? Couldn't be easier. Okay, but it's not so easy to do that. And here's why. To apply sigma, we actually need to know epsilon not from this formula that I gave you, but we need to know what it looks like as an actual element of this number field. Okay, and to illustrate why this is important, I'll give you a very similar looking formula. So suppose I give you this function of t, a of t. This is like generally a transcendental function, okay? It's an exponential of some integral, much like this simplified formula that I gave you before. And I say, hey, Alexi, please apply the Galois automorphism to this thing. Take a of 1 and apply the Galois automorphism that flips root 2 to minus root 2. Go.
So you go to Mathematica, plug it in, and better like give me this thing in terms of square root of 2, and then I put a minus sign.
You hope that it does that. And in fact, it will. But if you didn't have Mathematica, how would you do it?
That's cute.
You're in really deep trouble. Yeah, because I would also just ask Mathematica. So it's also not even clear, even if I were to promise you, like if I were to just promise you in advance that this thing has a representation over Q adjoin root 2, it's really not obvious how you would proceed. So does anybody know what the answer is? Unless you've just plugged it in, you probably can't guess. If you were to write out the decimal expansion of this is basically what Mathematica would do. It would guess, it would look at this and it would guess, hey, that looks like, it's not very sophisticated, right? It would guess 1 plus root 2, and then it would say, yeah, I think this is 1 plus root 2. And if I sort of keep evaluating it to more and more digits, it stays consistent with that. So just going to guess that's the answer. If you had some way to validate that, then you would say, okay, then the answer is 1 minus root 2, because I just flipped the sign of root 2 once I have this representation. But if I only have this representation up here, you're kind of toast. There's not much you can do.
Can you write down 1 minus root 2 using some similar integral?
No, if I knew how to do that, then like the next few slides would be pointless.
Does it even exist?
We don't know. We have no idea. We really have no idea. It would be remarkable if you could do that. It would be amazing, actually.
Yes.
No, anyway, yeah. So, okay. So to illustrate just how bad this problem is, okay, this map, this Galois conjugation map. So we're used to, so I said an analogy like complex conjugation. This is like a relatively smooth operation, right? You know, two adjacent points in the complex plane get mapped to two adjacent points in the complex plane under complex conjugation. That is really not true for points that are adjacent or nearby on the real axis that are of the form like a plus b root 2, where a and b are rational. If I pick, you know, let's say this point, this plot shows what it gets mapped to under Galois conjugation. And so some nearby point goes to some wildly different place. So this map is like violently discontinuous as a function of the points on the real line, right? This is not anywhere near a continuous map. Okay, does this look continuous?
I'm not sure.
No.
In this picture, so for any point on the x-axis, there's exactly one point in the.
Yeah, so I take, so this specific point is, yeah, it's crazy. It's insane, isn't it? Yeah, it's like it exceeded my expectations. I was like, I wonder how bad it really is. And then I plotted this and I was like, oh, it was worse than I had envisioned. Okay, so to combat this, we have this procedure that we call, so we have a ghost and we want to kind of like bring it back from the dead. But we have to do some like really black magic in order to do this, because we have to apply, we only have access to a transcendental function, but we need to do these like arithmetic algebraic operations on it. And it feels like black magic. So we called it necromancy. So we're going to like bring this ghost back from the dead and bring it back to life in SIC world. So the approach that Mathematica uses, by the way, is something called integer relation algorithms, which probably many of you here are familiar with, like lattice, like closest vector in a lattice type problems. Okay, so this is very closely related to that. I'm sort of shorter on time than I expected, so I won't go into too many details. But I'll describe this necromancy algorithm on the next slide. But we applied this necromancy procedure, avoiding using lattice basis reduction on very large lattices, which it would need very naively. And we were able to do it and construct 3 new SICs in dimension 100. So it's kind of a miracle. Like you look at this plot, and if these conjectures aren't true, there's something way crazier going on that we were able to like apply a numerical procedure that converts transcendental things to algebraic things, applies this automorphism, then spits out a SIC. Something way crazier than Zauner's conjecture is true if somehow Zauner's conjecture is false. So, okay. Maybe I'll just skip the slide about how this necromancy procedure works. It's a little bit complicated. And I'll just say we can, we have certain, yeah, maybe I will say just a tiny bit about this slide. So this twisted convolution conjecture, we can't really prove that pi squared, or sorry, upsilon squared equals upsilon, even though we can prove that it has trace 1 and that it's equiangular. So that's equivalent to saying like we can't prove that it's rank 1. But there's an alternative way for us to formulate this, which I say on this slide that we can sort of assume the twisted convolution conjecture, but there's another way to do it where we can use a formula with, this is like a, so remember this C is a square root of a root of dth root of unity. So with this 2 here, this is like an aliased discrete Fourier transform, right? I'm summing over K. This is a root of unity. This 2 part is a dth root of unity now. So it's like K times P2. So this is a discrete Fourier transform with some aliasing, okay? If I look at these transformed variables on these Stark units, then I can actually get something which is manifestly a rank 1 object, okay? So you might think that this sort of settles it because twisted convolution is there to try to prove that this thing is rank 1. But I know in terms of these Fourier transformed units and ratios of them that I can actually exactly construct a rank 1 object. But if I do that, I can't then prove that it's equiangular anymore. So it's a very deep sense of frustration that there's sort of two complementary approaches to try to do this, but we're in a jam either way.
Numerically, they're the same thing.
They're numerically exactly the same thing, and it's just really, yeah, it's so frustrating. It's so frustrating. What's nice about this formulation is I don't have to do d squared computations. I only need order d. So this is really nice. Okay. So you want to do this. So I'm going to do a special demonstration for Alexei.
And
I will share. So he wants to know, did you check this? Yeah, I did. So can you, yeah, no, I'll just,
Typing without seeing.
no, I've got it. Yeah. So here's all I typed. I typed using Zauner. It's pretty small. So there's a Julia pack. I've already got it loaded, so that didn't do anything. But I can say like d equals 7, q equals what was it, like 2, that's an example of one. So then I can say so this is a data structure that has all of this admissible pair stuff in it. It has the field, right? It's 8 instead of 2 in this example for some technical reason. It's not important. And then I can do things like compute the ghost. And there it is. There's your ghost, obviously, right? Or not so obviously. I can also do the following. I can apply necromancy to this thing. And it takes a second. But there it is. So V. So if this is really a ghost, then if I compute the trace inner product squared of this thing with all of its Weil-Heisenberg conjugates, so this is conjugating by the pth displacement operator P acting on that thing. Okay, so I apply the pth displacement Weil-Heisenberg displacement operator to the vector, and then I dot it with itself. And then because it's projectors, I need the absolute value squared of that. And that should always be equal to 1 over d plus 1. If I've done this correctly. So this is Julia, by the way. Oh, it says it on the prompt. So this should be true for all shifts, for all non-trivial shifts. And it is. So it is to like better than machine precision, to 78 digits of precision, right? So it worked. Okay, numerically. Okay, so yeah, you can just it's a free open source package. You can find it on my GitHub page. You can pull requests are open. I sort of said this already about how admissible tuples we conjecture. So this is a theorem if I drop this word inequivalent, but we need a slightly stronger conjecture than Stark, and we can prove, well, let's just say we conjecture that this is all the solutions, that this construction is sort of all of them. It would be very interesting if that were false.
wasn't there one exception that?
Yeah, but that doesn't have Weil-Heisenberg symmetry.
Oh,
It's
so
like an
all of them
exceptional.
that satisfy the well.
The Weil-Heisenberg symmetry. Yeah, that's right. And so this necromancy procedure is kind of crazy and really involved. But because we have this this computation in terms of admissible pairs, and we understand the algebraic structure of these things, we can answer questions conditionally that were completely out of reach of these sort of numerical methods. Like I can tell you conjecturally how many SICs there are in any of these dimensions, dimension 2 to the 50 or 2 to the 50 plus 1. Like I'm not using any special structure. There's this many inequivalent SICs in that dimension. In fact, it grows like the dimension of the underlying space. So there's lots of these things. Yes, but we think that that's probably all of them with maybe finitely many exceptions. If that's false, it would be extremely interesting. We can compute lots of algebraic data. I won't tell you what's on this table. It's just sort of like we can, these are all data that was previously empirical. We can now sort of write it down a priori and check after the fact. And then the last thing I'll say, do I have another 1 minute? Like, I guess we started 5 minutes late. Okay. We can generalize this. Instead of rank 1 POVMs, I can ask for like rank R POVMs. So D squared rank R projectors. And we get something similar called admissible tuple, where R features in the equation. Very briefly, the point of this slide is that I mentioned the importance of this star conjecture. One of the things is it informs this Hilbert's 12th problem, which is to try to classify all the abelian extensions. And so we can show that these things actually generate a positive fraction of all abelian extensions. So this is like a pretty interesting and new result. It's like progress on this Hilbert problem. It's conditional still on Stark, so it doesn't like solve even a 7.4% of a Hilbert problem, but it makes some interesting progress on it. So that's all I have to say. My conclusions here, I think there are a lot of interesting open questions here. Alexei asked, is it possible to just directly write down the formula without having to do this Galois conjugation? We have no idea. Are there non-Weil-Heisenberg covariant ones beyond this one special example that I cited? Can we prove any of these open conjectures? Yeah, maybe I think if we can't, if it turns out breakthroughs in algebraic number theory are actually needed to somehow solve existence constructively, maybe we should try non-constructive techniques. Like maybe we can construct these things, maybe we can prove existence of these things non-constructively using something like fixed point theorems, right? Which, or other sort of non-constructive methods. I'm cautiously optimistic that we will prove existence of an infinite family, but it still seems difficult. Thank you. Yes.
So I'm still confused about something. So can I give you now like D equals 217?